Okay, hi everyone. So I'm Yann. I'm going to be talking today about some work I've done recently with Edwin Fong, who's at Hong Kong, David Frazier, who's based in Monash, and my supervisor Jeremiah Knoblauch, with whom I'm at UCL. So I don't need to labor this first point too hard, I think. In Bayes, we start with a prior, we update it through a likelihood, we get a posterior. People like Bayes for a whole host of reasons, and Bayes admits some optimality properties, which we like. The only thing is that some of these optimality properties end up being derived from what we might consider surprisingly strict assumptions in terms of modern statistical machine learning, the most onerous of which being that the model is well specified. And we understand that if we violate these assumptions too gravely, that inference becomes brittle, and then so too might prediction. So something that people have proposed we do is we take the likelihood to some power tau, which I'll call the temperature, and bingo, we have our power posterior. And these things crop up a lot in statistics under a couple of different names, and like all good things in life have been rediscovered in machine learning under a different name. So these are called cold posteriors, and some of you may have heard of the cold posterior effect when talking about Bayesian neural networks. But the message is the same in both fields, subfields, that if you choose tau intelligently, you can robustify against the model misspecification. And so all of the literature really focuses on this central question, which is, okay, what does it mean to choose tau, this temperature, intelligently? And some people look at frequentist properties of the posterior. Some people are interested in matching the expected information gain we would get from a given experiment. These power posteriors are connected in a sense to pack Bayes and statistical learning theory. And there what you're trying to do is tune the temperature to optimize for a generalization bound. But then one corner of this, which is relatively underexplored perhaps, is choosing tau so that you optimize for predictive performance directly. And it's here that we're really going to be interested. And one of the sort of fundamental points that I'm going to try and get across today is that this is not possible, that this tempering has a vanishing effect on predictive performance, meaning that with high probability it kind of doesn't make sense to choose tau predictively, or that you can't. Okay. So how we're going to approach this problem is that we start with our power posterior, which we know and love, and integrating the statistical model over this, we get our posterior predictive. So for the time being, what we're going to do is consider that tau indexes a predictive distribution directly, just for simplicity. And then we're going to say, okay, well, I want to choose this tau then, such that I'm minimizing the distance between my true predictive and the posterior predictive that it induces. I'm going to keep the conditioning on the data here, just because I want to make it extra clear that the results I'll show you today are quite general and extend beyond IID sampling. So if you're doing temporal forecasting, this all holds. We make no IID assumptions. And likewise, we'll make no assumptions on the model being well specified. And what I'm going to show is that objectives of this kind are ill-defined. They do not admit a unique optimum. Instead, what you're going to find is an infinite range of tau that produce the same predictive performance. In a word, after some critical value, tau does not play a predictive role. Tau is not a predictive weapon in your arsenal. So maybe a quick numerical example to demonstrate this. This is a simple normal location problem. I sample data from a Gaussian with unknown mean. I estimate the mean. I predict future data. On the x-axis is the temperature, and the y-axis is this objective that I showed you before, scaled, just for visualization. I'm going to show this to you. Very faintly in gray are individual data replicates, and then in black is an expectation over data. And there are two important points on the x-axis, which is as you take tau going to 0, because all tau does is regulates the weight between your data and your prior, tau going to 0 just means that I'm sort of letting go of my data, and I'm falling back a lot more on my prior predictive. Likewise, if I take tau growing, I'm somehow drifting away from my prior, and I'm falling a lot more on my maximum likelihood estimate, and in turn inducing my what I'll call my plug-in predictive in this pretty violet color. And what I'm finding is that after some critical value of tau, any value that I choose induces the same predictive performance. In a sense, I know I'm not finding an optimum in these curves, either in the gray lines or in the black line. I'm finding an infinite range of functionally equivalent predictive distributions now. And so this observation motivates our primary technical result, which we're going to spend a little bit of time on just because it's a bit heavier than the last slide. So we're going to make two weak assumptions. Here they are. The first one is a weak technical assumption. It's a Lipschitz condition on the root density. It's weaker than differentiability and quadratic mean. Satisfied, for example, by any model having finite Fisher information at the true parameter value. In a word, it's satisfied really by any regular parametric model. So don't need to worry too much about this thing. There's some maths there, but it's kind of OK. And the second assumption just says the posterior concentrates. And under these two assumptions, with high probability, the total variation distance between the plug-in predictive and the posterior predictive induced by tau is bounded by this maximum of something to do with the frequentist convergence and something to do with the rate of posterior concentration. And this will hold uniformly over tau, taken on some open, bounded positive interval, and exponentially quickly in n, meaning that really very rapidly, the posterior predictive indexed by tau resembles the plug-in predictive, the maximum likelihood predictive. This bound might not be immediately intuitive, so I just kind of want to show you roughly how we get to it. The total variation distance admits a triangle inequality. Rather than study this, we actually consider the distances where we look at the plug-in and the oracle predictive, and in turn the oracle and the posterior predictive. Bound this by the squared Hellinger. That's where we leverage our first assumption. That gives us the first term, and then the second term. And the exponential term is just a function of how we define posterior concentration. Okay, but right, so what does this really mean? Tau is not a predictive weapon. This likelihood tempering does not help you with high probability under these assumptions, help you achieve superior predictive performance. And as such, you can't find an optimal tau. Instead, what you have is this infinite range of taus where you've essentially indexed the functionally equivalent posterior predictive distributions that are giving you the same predictive performance. That's what we saw in that big flat region in that first plot. And the other thing we saw is that this was holding both for those gray lines and for that black line. So we can show that as well, theoretically, that this will also hold an expectation over data. So this is just if you were to say, OK, but this just means your optimization problem is fragile. I'll just take the expectation. And I say, no, this holds more deeply. And at this point, you can also say to me, OK, well, Yann, this is some nice maths. I'll say, thank you. But then you might also say, if I wanted to do this in practice, I wouldn't use the total variation distance. I might do something a little bit more practical, like cross-validation. OK, so let's try this. We take now tau, such that we're maximizing the leave one out. And I'm just going to quickly show my notation. This p minus I is just the predictive induced by deleting the ith datum. I'm just going to optimize the leave one out log predictive. People call this the ELPD. Aki and Powell have done some great work in approximating this thing nicely, and we can diagnose it as we saw yesterday with Preto-Ks. This is all very nice. And if I try and choose tau this way, what I'm going to find is that for every optimal cross-validation tau I'm choosing, I'm achieving the same predictive performance, but with non-zero probability, I'm choosing tau equals infinity, meaning that this estimator, tau CV star, has infinite variance. So this is just another way of thinking about what if I ignored the fact that I've shown you those objective functions and I've shown you those two lemata and you still went ahead and tried it, you're still finding an infinite variance in that tau because after some critical points with high probability, it doesn't matter what the value is, it just has to be higher than that critical value. So tau here, the likelihood tempering is not a predictive weapon. And because here maximizing ELPD is somehow connected to minimizing KL, we can also show this under the assumptions before. Now we don't even need the first one. we can prove exactly the same conclusions we had before in a different distance metric. So this is holding beyond the choice of technical distance that we started off with. And at this point, it feels a lot like I'm just talking about methodology for power posteriors. But really, what I'm doing is I'm telling you that if you take tau equals 1 and you have your Bayesian posterior, so there's some notion of parameter uncertainty there, and then you're taking tau to be greater, all I'm doing is I'm shrinking that posterior uncertainty around the MLE. And I'm telling you that there's some infinite range of posterior uncertainties such that the predictive uncertainty isn't changing. Because these two distances I've looked at are both taking into account the uncertainty of the predictive. This is telling me that I can change the parameter uncertainty without changing the predictive uncertainty. So really, what we have here is a formal proof for the forecasting folklore that parameter uncertainty is not as important as data and model uncertainty when we care about predictions. And this can have some impact in practice as well. So for StanCon, maybe. Yesterday, we heard from Charles about finding out when an approximate inference scheme might be good enough. So for example, I think the case he used was variational inference, where we might be slightly underestimating the marginal posterior uncertainty. And this might say, well, okay, well, if you care about predictions, maybe this is all right. And then likewise, in Aki's tutorial on Monday, when we were doing the birthdays case study and doing predictive model validation with a model that takes too long to fit, using a pathfinder then, was kind of okay. It was still useful. And so there's some sort of connection between these two motivations. Okay, this is all in a lovely little paper on arXiv. Thank you very much for your time. I'm happy to take any questions. Yes?
So you said that starting from a critical value, it doesn't really matter. Are there relevant cases where that critical value is like substantially larger than 1, such that perhaps there could be better choices than not power scaling at all?
So in terms of finding when is your question more about identifying when that critical value is larger than 1, or?
Yeah, for example, how we can identify that critical value, how could we efficiently compute
Okay.
it, and that could still motivate us to deviate from the power scaling of 1 to at least the critical value power scaling.
Yeah, so we've done some analysis where we've taken, rather than looking at a fixed tau, we looked at a tau going to 0 at some rate. And there you can essentially choose where you want that critical value to be, but you do it at the expense of posterior concentration. If you take tau going to 0 at, say, rate 1 over root n, so that you would know that actually that critical value was 1 over root n, then what you're doing is you're slowing down the posterior concentration you have, because you're now combining the rate of tau, which is affecting how quickly you learn from the data, and that's inseparable in a sense from the epsilon n, which is the sort of unscaled rate of posterior concentration. Does that answer your question? Perhaps. We haven't found, I mean, there are also situations, of course, because our results are in high probability, there are always situations where you should not let tau just grow senselessly, of course. So this is by no means an advocation for letting tau just be massive. As I say, this was not a methodology paper. But because our results are in high probability, there are still situations where tempering can be predictive. Yes?
So this seems like a case like if tau goes to infinity, then we essentially get the maximum likelihood.
Yes.
So, right, everything concentrates, and it looks like what this is saying is just don't do Bayes.
No, that's good. This is not what that's saying.
Okay.
Because there's exactly this case where because our results were an expectation or in high probability, there are always going to be situations where you benefit from that parameter uncertainty. So this is by no means an advocation for just letting tau go to infinity. Again, it was not a methodological point. It was really just about trying to show how these different parameter uncertainty levels can induce the same predictive uncertainty.
So I'm a little bit intrigued get a result holds in expectation and with high probabilities. So would that mean that how far am I from that when I'm only looking at one realization of the data, which is what I'll have in most analyses?
So the question is then more about understanding when, diagnosing when this result doesn't hold.
Not really. It's more so the caveat you posed, but when answering the last two questions was our results hold in expectations
and in high probability.
So when I want to and then those results suggest large taus, and I want to understand better why in practice we deviate from what's prescribed in expectation and in high probability.
Okay, so I guess in the situations where you have small data, you can be relatively confident that these results, that some parameter uncertainty helps. So for example, were we to do, taken directly from Aki's BDA course, if we were to predict the number of left-handed people among, say, 3 or 4 of us, in this simple beta binomial example, that parameter uncertainty really goes a very long way in predictive performance. And then likewise, as the number of data you observe increases, that's the situation where the two sort of resemble each other fast.
So, we can take this offline, but so are your results more likely to hold asymptotically?
They are asymptotic results, yeah. They are in the, what we're saying is that for a fixed tau, or uniformly over tau, then as n goes to infinity at this rate, the two resemble each other, the posterior predictive and the plug-in predictive.